Welcome, everyone. So today we have our guest speaker, Greg Young, to talk about some of the latest and most exciting progress, at least in my opinion, in understanding deep learning. So as many of you have know that analyzing deep learning models from their infinite limit counterparts has been a hot topic in the last 2 years. Most of the work has been focusing on, as the model grows to infinity, the weights don't change, and therefore the analysis becomes a lot easier. But for a lot of practitioners, the majority part of why deep learning works is because the feature learning, right? So the previous work has been all ignoring that aspect. And today, Greg is going to actually tell us a lot about how to reconcile the feature learning part with analyzing their infinite limit with neural networks. A little bit more about Greg. So he is at Microsoft Research AI in Redmond. He obtained his bachelor and master degrees in math and computer science from Harvard. He was a recipient of the Hoover's Prize at Harvard for best undergrad thesis, as well as the honorable mentions for the Morgan Prize, which is the highest honor for undergrad in mathematics. His current research focuses on developing tools for understanding large-scale neural networks or computation graphs in general. So today, he will introduce his recent works on feature learning in infinite width limit. So go ahead, Greg.
Yeah, thanks so much, Jimmy, for a nice introduction. Let's just jump in right away. So as Jimmy introduced, I'm going to talk about feature learning in infinite width neural networks. And this is joint work with Edward Hoult, who was the AI resident at Microsoft during the course of this project. And this is part of the series on tensor programs that I'm writing. And I'll tell you a little bit about what that means a little bit later in the talk. But the outline for today is as follows. So I'll start by talking about the empirical side, reviewing the empirical side of deep learning, the recent progress, right? So, as we've seen from, BERT, for example, pre-training transfer learning is very, very important, and it's probably the biggest commercial aspect of deep learning applications these days. And I just want to briefly review what's happening on that side and why this requires feature learning. And then I'll jump over the fence to the other side, the theoretical side of deep learning, and talk about the most popular theory right now for understanding over-parameterized neural networks called Neural Tangent Kernel. And then finally, I'll talk about our proposal, the feature learning limit, which resolves the contradiction between the NTK theory, the Neural Tangent Kernel theory, and the feature learning. So over the course of this talk, feel free to pop out with any question you have, and let me know if I'm going too fast or going too slow. But this talk is aimed at a general audience, so I don't really assume very much background. So I'm gonna just go through and review the background before I jump into what we do in this paper. All right, so pre-training and transfer learning. There are two very prominent examples of this. One is, around 2012, we have the ImageNet dataset and models like ResNet, right, which allowed us to pre-train image models and then fine-tune them downstream to get like a variety of very nice image models, vision models for a variety of tasks. And then more recently, we have BERT and GPT-3 and other large transformers, right? We pre-train them on large language corpus. And this statement is kind of obvious to practitioners in the field, that pre-training and transfer learning cannot happen without feature learning. But as Jimmy mentioned, in the theoretical literature, if you just read the papers in the field, you don't get the sense. So at least there's apparent contradiction between the understanding across the fence. So in case there are those of you in the audience who feel this statement is controversial because you're maybe from a theoretical side, let me just pin down what I mean by this statement, right? So let me first clarify what I mean by feature learning, because this can mean different things depending on the context. So simply put, neural network can be decomposed into a body, which is like the part from the input layer to the last hidden layer, and then the head, which is the last linear layer of the neural network. And the body essentially represents a nonlinear embedding function from the input to the embedding, and then the head is just a readout, right? It's just converts the embedding to the output. And what I mean by feature learning is just that embedding function is learned. Okay, so people probably have seen these images before, but this is visualization of features from Resident 50 pre-trained on ImageNet from OpenAI microscope. So these different pictures correspond to different neurons, either in deep layer or shallow layer. And each picture corresponds to like the maximally activated image of a particular neuron in that layer, right? So for example, like this means neuron 4 in a deep layer can pick up like leaf patterns in the input, right? And then this is like, I don't know, starfish or something. And but in shallow layers, you have more simpler patterns, right? Like not so semantically complex. And my point here is just that, of course, like these, you will not see this pattern if you just take a randomly initialized Resident 50, right? So these demonstrates that Resident 50 definitely has learned some non-trivial features over the course of pre-training. All right, so coming back to the statement I made earlier, pre-training and transfer learning requires feature learning to work. So let me just briefly justify this statement. So in pre-training, again, you train on a large amount of data with a large model, and then in fine-tuning, you continue training that model, that pre-trained model on some specific small amount of data you actually care about, in the domain you care about. And usually what you find is that, continue training the pre-trained model will work better in the end than if you start from scratch training on your personal, your small data. And so let me briefly review how the fine-tuning works. So first, typically you discard the readout layer, the head of the neural network from pre-training, and you put on a new one. And there are two ways to do fine-tuning, common ways to do fine-tuning. One is linear fine-tuning, in which you only train the last layer, the new readout layer. Okay, so in this case, the simple insight is that pre-training improves linear fine-tuning, then the embeddings, i.e. features of inputs, must change during pre-training, right? And of course, this is just because, again, linear fine-tuning is just a linear problem, right? So if your features, your embeddings of the inputs are exactly the same as the random initialized embeddings, then you essentially haven't done any pre-training, right? So like the millions of dollars you spend on BERT is just for nothing. For total fine-tuning is another common paradigm to do fine-tuning. And so here, instead of only training the last layer, you train the entire neural network. So here, the insight is not as clear, but it turns out that you can get the same conclusion if you take the infinite width limit. But the argument is slightly more complicated. So I won't go into details here, but you can believe that the same insight holds. Okay, so that justifies why pre-training transfer learning really requires feature learning. So now I'm going to jump over the fence and talk about, briefly review the theory of neural tangent kernel, which is a very dominant theory in the field right now. So a neural network, a priori is quite complicated, and it's hard to really understand how it's going to evolve over the course of training, right? Because there's nonlinearities nested everywhere. And the theory of neural tangent kernel says, okay, let's be like a physicist, and when in doubt, just do first order Tate expansion. So that's what it does. So for example, here, F is a neural network, X is input, theta is a parameter. So this is just saying the change in the function, it can be written approximately as the change in parameters times the gradient parametrization. So using the definition of gradient descent, which essentially says, like the change in the parameter can be written as a linear combination of gradients at various times. We can write that the change in f is approximately equal to essentially a kernel times the loss derivative at that time, where the kernel is defined by this inner product of gradients and initialization. Okay, so this looks neat, right? It's a lot cleaner than you would expect if you just try to analyze neural networks as is. And it turns out that this approximate equals can be replaced with the equals in the limit of infinite width when when you're in a particular parameterization called the NTK parameterization. So that's very, very clean, right? And visually, you can interpret this as saying, suppose your loss is a square loss, then as the network becomes wider and wider, the optimization landscape, the function space become more and more quadratic, right? In general, for convex loss, it becomes more and more convex. So, this is a fantastic result in terms of analyzing the optimization of a neural network, as well as, to certain generalization results. For example, losses, square loss, and you can just interpret this the solution of this equation as a kernel solution, and you can use all the previous literature on kernel methods. So you gave us a lot of optimization and generalization results on neural networks, which is quite nice. But coming back to the topic of feature learning, the simple fact is that this particular theory does not allow feature learning. And I'll justify why briefly in the next slide. But the consequence of this is that, if you train BERT if you train infinite width BERT in the NTK limit, then you have wasted all your money, because it's as good as random initialization for fine tuning on glue or super glue or whatever, right? So this really, really contradicts probably the most important aspect of deep learning in practice today. Okay, so let me just briefly mention why NTK does not learn features. Some of you probably will find this very obvious, but let me just briefly say this for the other half of you probably. So the reason is just that we had to go through first order tail expansion for NTK to derive the NTK limit. And of course, for the tail expansion to be accurate at all, you want the change in parameters here to be small, right? And if changing parameters is small, then that means that embedding function cannot change too much. So the fact that we assume that tail expansion holds means that we're in a regime where the parameters just don't change very much. And as such, the embeddings cannot change very much. And embedding is not changing, of course, means feature is not changing. So that essentially is the intuitive reason why feature learning doesn't happen. Of course, I'm kind of being hand wavy, but just giving you the outline of how the argument will go. But you can make everything quantitative, make everything rigorous, and the argument will still go through. All right. So that was all review up till now. Hopefully, everybody's okay with this. Feel free to shout out any questions if you have any. So next, I'm going to give you a concrete example of the non-feature learning of NTK. And this is through the example word of X. So in case you guys don't know, word of X is an early example large-scale pre-training in language. And you can think of it as a precursor to BERT. So in word of X, you try to learn word embeddings, so vectors associated to words, such that semantically close words correspond to geometrically closed vectors. And here we train three kinds of models. So these are three plots corresponding to three kinds of models. So we train a 64 dimensional word of X, which is just the normal word of X. We train the NTK limit of that. And then finally, we train the infinite width feature learning limit that we propose in our paper, right? Which I'll explain later what it is. But here, just assume that it's well defined. And each plot here represents the PCA to 2 dimensions of the embeddings. So in particular, this is a 64 dimension projected to 2 dimensions, but the left and the right are infinite dimensional embeddings projected to 2 dimensions. But PCA still makes perfect sense. It type checks whether the original embedding is finite or infinite dimensional. So this is one fair way to look at all three in the same plot. Okay, is there a question? Okay, so Mika asked, what is the training loss in word of X? So here we're using contrastive loss, where essentially you try to train the network such that if you randomly sample a sentence and you randomly sample a word in the middle of the sentence, then the word embedding in the middle of the sentence, the word in the middle of the sentence is close to the average embedding of the context. So that's essentially it. Like and what you do is you take the inner product between the center word embedding and the context average embedding, and then you apply the logistic loss to that. And okay, so it's a contrastive loss. So that's like the positive case, and the negative case is that you randomly swap out the middle word with a random word, and that's a negative case. And then just a contrastive loss. Okay, so back to the topic at hand. And so could you explain why that would lead to such semantics in the embeddings for width, 64 dimension, and infinite dimension? I mean, I think so. Contrastive loss is very well known for doing like representation learning. So word-to-vec is a very early example of this, but more recently, if you follow self-supervised learning in vision, that's I mean, most of them use contrastive loss. I mean, there are also some new innovations using other losses, and I mean, you can also kind of interpret like BERT training as like mass language models as contrastive loss.
Is it possible? Maybe it's going to be easier to explain. Is it okay if I ask a question?
Yeah, of course. Yeah, feel free to shout it out. You don't have to type it.
Given the contrastive loss, which is common and very useful that you described, the task here was basically you project a city and a state, and you show here that the states and the cities are basically semantically separated for if you do a PCA for width 64 and for the infinite width. And to me, it's unclear why would such a contrastive loss, as you described, which is the middle word should project or a word from a sentence should project near the mean of the embeddings of all of the words in the sentence. Why would that lead to such a semantically meaningful division in the latent code, which is semantically for us, but I am not sure why would the model choose such semantic.
Yeah. So I mean, that's a good question, though it's not quite like pertinent to like the contribution of our work. So the answer to your question will come from the original word-to-vec paper, and there I think the answer, I mean, intuitively, it's just that like I mean, usually like words that appear together, like co-occurrence, usually is indicative of so you have to be very careful here. Like it's not, it's like maybe think about here like the specific notion of semantic closeness as just co-occurrence in some sense. Word2Vec actually is very bad, for example, just as a counter case to what I'm saying, is actually bad at telling apart like positive and negative things. Like you will actually cluster together positive and negative things because you cannot like the co-occurrence data for positive and negative things are actually very similar. But you can tell like different categories of things apart because the co-occurrence of different categories of words are very, very different.
That was my question. This looks like it actually discovered a category, even though it could be that a state and a city would actually appear together as opposed to a state with another state and a city with another city. So I don't see why would that division in particular arise.
No, I would say that city and states, they like are quite different because like, let's say you say like Washington, DC. You usually don't say DC. I mean, okay, that's a bad example, but like, I feel like a lot of cases, you will say the city, like Seattle, for example, but you're not gonna say Washington. Like Seattle has a very specific, like for example, Seattle is a tech center, consisting of Microsoft, Amazon, and so on. But usually you don't say Washington is a tech center. Like there's a very specific meaning attached to cities versus states. They're not swappable. That's what I'm saying. Does that answer your question? Okay, cool. All right, so let's move on. Anyway, so the point here is that yeah, we have two kinds of words here, color in two different colors, and in the middle, which is regular word2vec, we see that they separate into clusters, as indicated by our discussion with Mika. And but if you look at the NTK limit of this, there's no such separation, right? Like it's all clustered together. This means that word2vec in the integer limit doesn't pick up any semantics from pre-training. Now, if you look on the right, the feature learning limit, which we propose, you see the same pattern as the finite-width neural network, right? The words are now separated into their own distinct clusters. And in fact, even more so because, I mean, just visually, you can see that like this line here will separate the two clusters a lot better, more cleanly than the finite dimensional case. But that's just a visual indication. But we can actually look at some concrete numbers on downstream tasks just to confirm our visual intuition. So word2vec is commonly evaluated on the task called word analogy task among many others. But this is the famous one which asks the kind of question, what to a queen is a man to a woman, right? And the answer is king, of course. But the way you answer this with the word embedding is that you take the embedding man, subtract the embedding woman, you add the queen, add the embedding queen, and that's a linear combination of word embeddings. And then you look at which word in your vocabulary has the closest embedding to that linear combination. Okay, so this plot summarizes the performance, the test set performance, downstream test, the downstream task performance of different kinds of models. So on the x-axis, we have the training epoch, and then y-axis, we have the accuracy. And we have different curves here, where the solid curves are finite dimensional models from 64 dimension to 224 dimensions. And then the black dash curve is the infinite width model at the very top. And then the purple dot dash is the NTK limit at the very bottom. Okay, so looking at this plot, we can derive some observations. So the first is that if you look at the NTK limit, it has trivial performance, right? It's sitting at 0, and that's just because, like we said, NTK limit essentially doesn't learn any features over the pre-training process. So in the downstream task, it's just randomly guessing, and as a result, the vocabulary size is so large that the accuracy is practically 0. And then the other thing we can notice is that if you look at any vertical slice, you'll see that the performance is monotonic in width at any time during training. And the intuition here, oh, sorry, not the intuition here, but just to explain what this means, right? It just means that as you increase, as you get the darker color as you go up, right? The color increases. So this indicates wider models. And then the pattern continues until you hit the infinite width limit, the feature learning limit, right? So what this indicates is that our notion of feature learning infinite width limit is the well-defined, like a good notion that really captures the right behavior such that wider models do better, right? I mean, that's always a desirable property, like wider models do better for a definition of infinite width limit. Yeah, okay, so here width refers to word embedding dimension, right? Yes, yes, so width is equal to the word embedding dimension. Yeah, okay, so this is some results on word2vec, and we also have results on meta learning using MAML, and the conclusions are essentially the same. So I'm not gonna actually delve into that. You can check the paper for details if you want. But instead, I'm gonna go on to describe what the feature learning limit is. Again, feel free to shout out any questions. You can type your question as well, but I guess it's not as convenient for me to check the chat. Okay, so let's start. So I'll start actually by prefacing our discussion with the perspective parametrizations. And in my investigation, it turns out that that the perspective parameterization is actually very, very useful for understanding these infinite width or infinite whatever limits. And the intuition here is that for infinite width limit to make sense, to be natural, I mean, usually it has to be induced by some neural network parameterized, some finite neural network parameterized in a certain way, and you let the width go to infinity, and mathematically you get the infinite width object, right? And if it doesn't arise from such a parameterization or some natural way of dealing with neural networks, then it's not a natural limit to look at in the first place. And conversely, given some parameterization of neural networks, you let the width go infinity, you get some infinite width dynamics, right? So there's like this correspondence between finite neural network parameterizations and infinite width neural networks. And just to be concrete, what I mean by parameterizations. In our paper, there's a formal notion of like general parameterizations, which encapsulates all the parameterizations we've seen in the literature. But what I said earlier holds in general, like it's the intuition holds in general for more general notions of parameterization. But concretely, in the paper, parameterization is a package of how do you initialize your neural network, how do you pick the learning rate, and certain insertions of multipliers in different places in the neural network. So by multipliers, I mean like constant scalars. So for example, like softmax temperature is a multiplier in the output of the neural network. Attention scaling is a multiplier, in the dot product of the key and query in the attention, right? So you can see what this means. Okay, so NTK in particular is an example of this paradigm. So in the NTK example I gave earlier, the NTK limit is induced by the NTK parameterization, which I didn't actually tell you very much about, but there's a very specific parameterization that induces NTK limit. And if you use a different parameterization, you will not get necessarily get the same limit. And this is very important, of course, because the feature learning limit that I'm going to tell you about is induced by something called the maximum update parameterization that we also propose. In fact, we derived in our paper, which is not really in the literature so far. Like for one hand layer case is okay. So John asks, did you explain the methodology for infinite dimension word embeddings? How did you practically implement it? The answer is I have not, but I will toward the end of the talk. So the plan is I'm going to tell you how to define the limit by defining the parameterization, and then I'll tell you how to take the infinite width limit of the parameterization, and then from that you will be clear how I implemented the word-to-vec infinite width word-to-vec experiments. Okay, so I will tell you actually what maximum update parameterization is in the next slide, but for this slide, let me just pull back, zoom out, and give you a bigger picture kind of the universe of things, and so to give you context of where we're standing at. So like I said, in the paper we have a formal notion of parameterization which encapsulates essentially everything we've seen in the literature. So we can ask, what does the space of parameterizations look like, right? And again, this tells us where we're standing, where we should be going within the space. So the picture of the space is very interesting. First of all, if you throw like a dart in the space of parameterization, so you essentially pick a random parameterization from the space, you're most likely going to pick an unstable or trivial parameterization. So what that means is, unstable parameterization, you're going to blow up, your SGD is going to blow up very quickly in the infinite width limit. And in the trivial parameterization, your SGD is going to get stuck at initialization in the infinite width limit. Okay, so neither of them are good. So it's only meaningful to look at the complement of such parameterizations. And these are the non-trivial stable parameterizations. They form a high-dimensional polytope in this space, in this larger space. And within this polytope, the feature learning parameterizations form two facets, right? So this is indicated by the thick brown lines, and everything else is in the kernel regime. A question? And the kernel regime here means that so yeah, I don't actually want to write on my PowerPoint because it froze for quite a couple times now. So but kernel regime, what I mean by kernel regime is just that if you recall earlier, in the NTK case, you have the equation that the change in the function is equal to kernel times the loss derivative. So essentially, kernel regime here means that change in the function is equal to some kernel times the loss derivative, where the some kernel is fixed over time. So essentially it means that the solution is induced by some fixed kernel. Okay, so so this definition actually makes it a bit more clear that this picture is actually kind of not trivial, because kernel regime is actually not by definition the complement of feature learning. It's like kernel regime means a very specific thing, that like evolution of a function in function space follows like kernel dynamics. Whereas feature learning here means that your essentially your features change by a non-trivial amount. So okay, so that's a basic picture, and there's some interesting consequences just from looking at this picture. One is that if you want a non-trivial Gaussian process initialization, like in the refer-neo sense, then the parametrization that leads to that cannot allow feature learning. So this is so just take a minute to grok this, but this is saying something I think quite surprising from like Bayesian point of view, or from a practitioner's point of view, right? So he says, for Bayesian people, they often want to use the randomness of the neural network initialization to give you some gauge of uncertainty that you can use for quantification uncertainty. But this is saying that if you want to allow this, then you're parameterizing your neural network such that it doesn't learn features, at least in the infinite width limit, right? And here in the picture, this is indicated by the disjointness of this purple triangle here, which indicates the parameterizations inducing non-trivial initial GP and the feature learning regime, right? So that's kind of an interesting consequence of this dichotomy. Unfortunately, I don't have time to go into the details of this, but feel free to ask. The other thing that's interesting is something is missing in this picture, which is kind of like something you expect in between kernel regime and feature learning, which is like higher order kernel dynamics. So again, unfortunately, I shouldn't try to write on my PowerPoint. So let me just describe this verbally. By higher order kernel dynamics, what I mean is that like the change in the function is given by like a higher order kernel contracted with like loss derivative to some higher tensorial power. So where compared to the kernel regime as defined here, which is that the change in the function is equal to a rank 2 kernel times the loss derivative. So John asks, what does LR stand for? The LR is learning rate. So yeah, so in particular, if you look at standard parameterization, if you use a constant learning rate, so constant here meaning like it doesn't depend on the width of the neural network, then it's actually unstable, in the sense that again that if your neural network is very wide, your HDD is going to blow up very quickly. And this is something you can try at home, of course, and you can verify that's true. And you can fix this by using a smaller learning rate, so scaling like 1/width, in which case standard parameterization is stable and non-trivial, but it will land in the kernel region, so you will not learn features in the infinite width limit. And maximum update is the only or like it's the optimal feature learning parameterization, essentially in the sense that like all the layers will learn features. And if you know something about mean field parameterization, they are not exactly the same, but they're equivalent when depth is equal to 1. As in equivalent as in they produce the same trajectory of in the function space. Okay, so finally, let me go to the definition of the maximal update parameterization. So the easiest way to describe this is to modify standard parameterization. And there are two modifications. The first and the most important one is in the last layer. So here with n, denoting the width of the neural network. What we do is divide the logits by square root of n, and we use a constant learning rate for the entire neural network. Okay, so concretely in math, what this means is that the output of the neural network is equal to 1 over square root of n times the weights, that's last layer weights, times the last layer embeddings, where the last layer weights is sampled according to a fan-in initialization as usual. Okay, so this turns out to enable feature learning by itself. And the intuition you should take away here is that in the standard parameterization, your last layer has problems. So one is initialized too large, and two, it gets too much gradient. And what that means is that if you want to use a very large learning rate, the last layer is gonna kind of blow up, make things blow up very quickly. And because the last layer is getting so much gradient, the learning rate has to be small enough that last layer learns, but the previous layers don't learn enough to enable feature learning. And this modification fixes that problem. So the 1 over square root of n essentially makes initialization smaller and also makes the gradient smaller, which allows you to use a larger learning rate. Okay, so this is the most important modification, but we also have a modification in the first layer to make sure that this is a maximal update parameterization. So here we multiply pre-activation by square root of n, and we use fan-out initialization. So concretely, we set the activation, so pre-activation of the first layer equal to square root of n times the weights times the input. And the weights are now sampled with fan-out initialization. Okay, so fan-out again is 1 over n is the width, which is the fan-out of the first layer. And the intuition here is that the standard parameterization has another problem, which is that the first layer weights gets too little gradient. And as a result, like even if you allow the body to learn features, the first layer will still get stuck in initialization. So this modification just makes sure that first layer also learns features by increasing the gradient by an order of n. Okay, so all other layers are same as standard parameterization, just fan-in initialization. There's no multipliers, and altogether these enable feature learning in every layer, which is why we call this maximal update parameterization. Okay, so this is to recapitulate, right? Again, the feature learning feature learning limit that I've been talking about in this paper is defined as the infinite width limit of this maximal update parameterization. And again, the maximal update is called maximal update. It's kind of like optimal in a sense because it allows features in all layers to be learned. Okay, now in the rest of the talk, I'm actually going to tell you what the limit looks like, right? So all I've done is just defining what it is, but I haven't actually told you what the infinite width neural network actually does. So here, unfortunately, we don't have a very easy description compared to either the ReferNeo or NNGP description, neural network as Gaussian processes, or the NTK description, which is neural network as kernels. So the best thing that I've come up with to convey the main idea is to tell you like how the computation goes. How do you do the analysis yourself to give you some intuition for how this works? Because whereas like in the one hidden layer case, there is like some nice intuition. For the deeper case, that intuition breaks down. So so to give you the general idea, yeah, the best thing I've come up with is just to give you the intuition behind the calculations. And the main philosophy behind such calculations is as follows. When the width is large, every activation vector has roughly IID coordinates at any time during training. Using a technique called Tensor Programs, we can recursively calculate such coordinate distributions and consequently understand how the neural network function evolves. Okay, so if you've done NNGP or NTK before, the first instance probably sounds familiar if you replace at any time during training with initialization, right? Because initialization, you have a lot of randomness, and you can apply like central limit theorem in a recursive way to get approximately the statement. But the surprising thing is that this observation actually holds at any time during training, and you can propagate the randomness initialization very deep into the training procedure. And the way you propagate such randomness is you use tensor programs to calculate the coordinate distributions. Okay, so this is a very high level statement, and I don't expect you to get very much out of this. So let me actually delve into a concrete example to realize this notion. Okay, so the simplest example we can go to is a linear 100-layer neural network. And for simplicity, assume input and output dimensions are both 1. Okay, so in this case, of course, the output of neural network can be written as just a matrix multiplication, right? Like a row vector times a column vector times the input, where the blue vector is the first layer weights, the green vector is the second layer weights. Okay. So mathematical parameterization dictates that you initialize the weights with ID coordinates with Gaussian with mean 0 and 1/n, 1/width variance. Okay, so then with this, we can see that f, the output of the function, will actually converge by low large numbers to a deterministic quantity initialization. So I mean, just because f again is the contraction of these two vectors, you can write it as a sum of large number of random variables. Each of them has scale 1/n, and then you can write it as a mean, right? And you can apply a lot of large numbers. All right. So then, if f, the output of the function converges, the loss derivative also converges, because usually loss derivative, like the L prime, is continuous, right? Like think cross entropy or square loss. It's a continuous function. All right. So this I don't know, like salmon color square or scalar, it will converge to a deterministic number in the infinite width limit. Okay, so far so good. Like again, feel free to shout out any questions if you have. All right, now let's look at the backward pass, the first backward pass. And if you do a little bit of calculation, you'll see that the gradient of the second layer weights is the first layer weights times the loss derivative and the input, right? So 2 scalars. And likewise, the gradient in the first layer, second layer weights times these 2 scalars. And because I said earlier that this scalar converges deterministically, and also remember that the weights initialization are ID by by definition, we have that the gradients of the 2 layers are both approximately ID, right? And as such, when you do the gradient update to the weights, you maintain the property that the weights have approximately ID coordinates, right? And here, what I mean by approximately ID coordinates, I mean within each vector, each entry is approximately ID, but there can be correlation, and usually there is, between corresponding entries in the weights in the first layer or second layer weights. So like like this neuron, the first neuron of the 2 weights are usually correlated in the same way as the second neurons in the 2 weights are correlated, and so on and so forth. But the pairs of neurons are IID, approximately IID. Okay, so that's the basic intuition. And okay, yeah. So before that, let me say this one thing, and then we can continue. So from the derivation just now, it should become obvious that, hold on. It should become obvious that linear combinations of the weights in the second forward pass, and in general in the teeth forward pass, are linear combinations of weights from initialization. And this fact we'll not use right now, but we'll come back to this later. Okay, so now let's continue. The output of the function converges by low large numbers for the same reason as before, right? Because the weights are approximately ID. And by same reasoning, the loss derivative converges. And then the gradients are both approximately ID. And you can see the pattern, right? Like you can repeat this for all times. So the point of the previous section is to demonstrate this statement that when the width is large, every activation vector has roughly ID coordinates anytime during training. And in our example, the activation vector in the first layer is just the first layer weights times the input, which is essentially just the first layer weights, right? And as justified just now, the first layer weights are approximately ID. Okay, so hopefully that gives you some intuition why this is true. All right, now let's actually do some calculation and eventually try to derive the algorithm to compute the word-of-back experiment. All right, so in this example, we earlier made the observation that weights at any time are linear combinations of weights from initialization, right? And let's take advantage of that observation. So first, let's give it some notation that U denote the first layer weights and V denote the second layer weights. And then let the weights be initialized again with zero mean Gaussian with variance 1/n. And let UT and VT denote the values of U and V at time t. And with if I don't use subscript, it means initialization time. Okay, so our earlier observation implies that there are coefficients AT, BT, CT, DT varying with t such that VT can be written as A times V plus B times U, where V and U here without subscript again means V and U initialization. And likewise, U is equal to CV plus DU. Okay. And these coefficients are going to be random variables with finite n, but they're going to converge to deterministic values in the infinite width limit. And the initial condition for A, B, C, D is just A and D are 1 and B and C are 0, right? This just says that initialization B is equal to V, U is equal to U. Okay, so suppose we have these expressions for VT and UT, then the output of the neural network can be written approximately as AC plus BD times the input psi. In the case when the width is large, and this is just because when you contract the VT and UT, the cross term involving U and V and U, they will vanish because like the initialization they're sample independently, U and V are sample independently with zero mean. But the VV term and UU term will lead to the AC and PD. Okay, so there's some simple arithmetic you can do. And the point here is just that to compute the limit of the function f, the neural network function, it suffices to compute the coefficients A, B, C, D. Okay. All right, so now the task is to understand how A, B, C, D evolves. And here I'll just briefly give you some general notion of how that goes. It's actually quite simple. I think giving you the general notion should give you enough idea to replicate it yourself. But the point here is that given VT and UT are of the form as indicated earlier, you can find out what the gradient looks like, which you can again express as linear combinations of V and U initialization. And as such, when you do the gradient update, you can line up the coefficients of V, line up coefficients of U, and that tells you how AT plus 1 relates to AT, and BT plus 1 relates to BT, and so on and so forth. Okay, so just to summarize, what we've done here is derived the feature learning limit of a linear 100 layer neural network, the simplest case. Okay, so this is like much easier than the general case, but it's perfect for giving a general notion, the general intuition behind the general case. So here in our example, we have input and output dimension equal to 1, linear equal to 1, so that in the infinite width limit, the function output at time t is equal to AT CT plus BT DT times input. And then ABCD are updated like this. And then ABCD initialization are given by this. Okay. All right. So you can take like a minute or something to grok this. But let me digest this for you. Actually, there's a simpler way to look at it. Look at this. That's actually quite useful. So if you look at this equation for FT, you see that this is actually a linear one-hidden layer neural network with two hidden neurons, where like A and B, two scalars, indicate the second layer weights, C and D indicate the first layer weights. And ABCD, the initialization is instead of random initialization, is like a diagonal initialization where ABCD is equal to identity matrix. So we can speculate that the feature learning limit of a linear one-hidden layer neural network with random initialization is equivalent to a with D plus DL linear one-hidden layer neural network with diagonal initialization, right? In the sense that like training the object on the left gives you exactly the same function as training the object on the right. And here D and DL are 1, right? So this corresponds to 2, which accords with our observation here. And of course, this is true in general for general D in and D out. And this is what we do actually for word2vec. So word2vec actually can be written as training a linear one-hidden layer neural network, where the hidden dimension embedding is the word embedding. And concretely, the D and D out are vocabulary size in the word2vec example. So on the 2 data sets we used, the sum is 140K or 280K. So we ran this on like on a 128 CPU large memory machine on Azure for like a week or something to get the results. Okay, so to summarize our example, what we did is, we observed that the weight matrices have ID coordinates and initialization. The function output converges due to law of large numbers. The gradients have approximately ID coordinates. And finally, so after the gradient update, weight coordinates are still approximately ID. And then you can repeat this reason. And in the linear case, we express the weights at any time as linear combinations of weights from initialization. And this allows us to have efficient calculation of the limit. Okay, so this finishes the one-hidden layer example. Let me pause here in case anybody has questions. And then essentially, I just have a couple slides on the general case, and then I'll wrap it up.
So I have a question.
Yeah.
So you have shown established the training dynamics of essentially the equivalence between a random initialization and this like 1-0 identity initialization. Can you say something about how we can go from this per time set dynamics to its stationary point if we run the dynamics to infinity?
Yeah, for a long enough time. Yeah. So let me see. So I haven't thought about too much about this question before, but my hunch is that there's a simple answer to this, and I think you're gonna get some kind of like matrix factorization kind of thing, like you're gonna get some result like the first layer and second layer weights are kind of like is like some minimal NOR solution to some matrix factorization, like essentially conditioning on the product of them equals like the co-occurrence data for the words or something like that. Like that's my hunch. I think the answer is like in that ballpark.
Okay.
Another question in the chat. Okay, yeah, thanks, Albert. All right, so let me just quickly finish, and then I'll leave some more time for the questions. Okay, so the one-hidden layer case is actually is like the really simple and doesn't actually require a lot of machinery behind tensor programs. Whereas the deeper case is really like a lot of really heavy math goes into. So let me just tell you like what kind of complexity lies behind the deeper case. But if you're interested, of course, go to the paper for details. So the complexity here is that you have these n by n Gaussian random matrices in the middle of the neural network, and that's very different from in the one-hit layer case where like the weight matrices are essentially one side is always fixed, right? It's finite, like either output or input dimension. And these n by n Gaussian matrices have very different properties than those kind of like vector-like matrices where one dimension is finite. And you can roughly, categorize the behavior of this W into two parts. One is the central limit behavior, where essentially if you multiply W by a vector which is sufficiently independent from W, you get a Gaussian vector, right? So this is like the most straightforward part of the behavior W. If you've done a Gaussian process before, neural network Gaussian process before, this is should sound familiar to you. The other part, which is much more complicated and requires a lot more mathematical machinery, is the correlation with W transpose. And so if you only do like one step, actually this actually doesn't come up. So like NTK essentially doesn't actually is affected by this correlation. But if you take more than one step in the feature learning limit, where you're taking large steps, this correlation between W and W transpose quickly adds up, and it gets nested very quickly. And this really requires a lot of mathematical care to calculate this correlation. Okay, so if you are familiar with AMP from compressed sensing, which don't worry about if you don't know, but for those of you who know, analyzing neural network training is similar to AMP analysis, but you don't subtract the on-sider correction term. But ignore this if you don't know anything about AMP. Okay, so and see the paper for more details of the Elton layer limit. Okay, so the whole example we did, and there's a deeper deeper case overview that I just did. They're just intuitions, but you can formalize everything in this framework called Tensor Programs, and it automates all of these derivations. So essentially, you just have to follow some recipe, and you can get the limit mechanically. So one way to think about this framework is that it's a kind of compiler that compiles any finite width computation to infinite width computation. So like in fact, it is possible, and it's on the roadmap somewhere, to write an automatic program to convert your PyTorch code to code that runs infinite width neural networks. And just to make the notion of tensor program a bit more concrete, you can also make the analogy of tensor programs with linear programs in the following way. In linear programming, usually you have some problem, like a flow problem of some sort. A priori doesn't look like any linear problem, but once you actually express this original problem in the language of a linear program, you can use the solver, right, to solve the linear program and get the answer you want to the original question. And the tensor program framework is similar in that respect, in the sense that suppose you want to understand some really wide neural networks, or it's just some neural computation in general. As soon as you can write that form of computation in the specific form of tensor program, you can ask the quote unquote solver to solve the limit for you in a mechanical way. And then that gives you the answer to your original question. Okay. Okay, so if that interests you, please look at the paper for more details. And that's it. That's my presentation. Thanks, everyone. Thanks, John. So yeah, feel free to ask any questions. There's a longer talk with more details in the archive paper in case you want to scan the QR codes.
Great, thanks, Greg. We can probably take 1 or 2 questions from the audience. So I guess another question of mine is, how does different, let's say, activation functions and losses, affect the analysis and the compilation of the tensor program? Does one loss or activation function induce more approximation errors than another?
Oh yeah, yeah, for sure. So as a basic rule of thumb, like the higher degree your like if like the faster the nonlinearities grow, for example, like quadratic or cubic or something like that, the more deviation there is to the infinite width limit. So like if you want to be close to your infinite width limit, radius is a good choice because it's linear. But definitely stay away from quadratic. But anyway, nobody actually uses that anyway. But I think that's also because it's like far away from the infinite width limit that people don't use it. The other thing is so earlier essentially with the growth I was talking about the forward pass, but in the backward pass you also got to be careful because if you have tangent, then what happens is that if you have to be careful essentially about the saturation gradients. And if your neural network is kind of narrow, then in some sense you have a lot of noise. And that means that like the pre-activations can have very large variations. And that variation can push you into the saturation regime where you get very little gradient back. So like that means that you're kind of far away. You're gonna be farther away from the infinite width limit because your gradient is very different from what we would be in the infinite width limit. So for the gradients, you have to be careful not to use saturating nonlinearity. So it turns out redu kind of is like good for both of these.
Right, that's neat. So I was thinking like if you have very deep networks with 10H activations, like eventually through many layers of propagation, probably won't get a nice form that you previously.
Yeah, that's right.
Okay, that's thanks Greg for his wonderful talk. And if you have any questions, feel free to send me an email. I'm sure he'll respond with great enthusiasm.
Yeah, thanks, Jimmy. It's been a pleasure.
Great.
Yeah, thanks everyone. Have a good Friday. See you later.